All right, here we go. Here we go. So you guys should all have your mass and change notes out. This is a lot of stuff. You might be confused as to what it is. But we started at the very beginning. We talked about changes, physical changes, chemical changes. So we had these notes down. And then from there, we went and actually did the mass and change lab. I just wanted to show you what they look like. So after this, what we did is we actually did the lab. We had our mass and data worksheet. That will be included with the notes. You were supposed to also write down observations about what you noticed when you were at the station observing the change. And then we put all our class data together. So all that stuff, there's really going to be like 4 parts to these notes. So the first notes that we took, the mass and change data worksheet, the class data, and now this. All right, so the point of this today is I'm going to talk about what I think should have happened, talk about some things that you need to consider when you make models, and we're even going to lead into a new modeling norm. So these can go right with your other notes to continue. So station 1, first of all, we are burning a wood splint. So anytime you're burning something, that's going to be a chemical change. And in terms of mass, what we noticed was that we lost mass. But here's something to consider. Whenever you're burning something, heating something, but especially burning something, you are going to have oxygen involved because what it's called is a combustion reaction. Okay? So one thing that can actually happen in these types of changes is we can actually notice a mass increase because particles will be coming in from outside and coming in. All right? So this was a model I made earlier, kind of lame. But I just trying to get the point across real quick. But we had wood splint over here, which I should have always include labels. So whenever we use labels, it's a good idea to use the labels on the big things. And then save the key for your dots, your particles. Okay? So I made a little key here. I put wood particles, I made them black. Oxygen particles, I made them red. I know it's harder for you guys because you don't have different colored markers and stuff. But what you can do is you can do dots and then little circles, which are kind of like white dots. If you need to make 2 different types of particles. I should always title it in before and after. All right. But really what we got to consider is we got to consider that any particles I show in this before picture, I should show them in the after picture as well. All right? Yep, you should be writing all this down. And now we did show a loss, okay? So that makes sense because you may have noticed in this lab maybe there was some smoke coming off it, so some particles that were leaving. We also know that there's probably a good source of error. The ash is very light, so it's possible that it kind of blew off the watch glass. We lost some of the ash. So it makes sense that we're probably going to see a mass and change where mass decreases. Okay. So just kind of one more time to restate what I was saying. If you notice in this first picture, I drew 3 red dots. I drew 5 black dots. In the end, oops, I made too many. In the end, there should be 3 red dots and a total of 5 black dots. Okay. What about the second station? What do you guys think should have happened there? First of all, what kind of change was the second station? The melting ice. Is that a physical change or a chemical change? Physical change, all right. Should the mass have increased or decreased or stayed the same? Stayed the same? All right, cool. Let's scroll down to station 2. All right, so it is a physical change, mass stays the same. We only have one type of particle in this model. Just H2O is all we're really concerned about. That's all that's involved. And that's a good idea. Whenever you're doing modeling and you got to show the particles, try to think of all particles involved, not just the ones you can see, but also the ones you can't see, like invisible, like air a lot of times. Gases in the air, people forget to include those in models. And you have to include them if it's important. All right, like in melting ice, maybe I'm not showing all that. But what I did here is I drew some cubes in the before picture. I put 2 dots in each cube. So in the before, there is a total of 8 particles. And this is my after right here. And so I changed how the particles are arranged, but there's still 8 particles. Okay, the shape changed, the volume might have changed, so the size of it. But it's still just H2O, and that's why it's a physical change. We're not making any new substances. There's no chemical reaction going on. It's not blowing up. We're not seeing energy released or bubbles produced or precipitates forming or color change or anything like that. All right? It's just melting ice. So all the particles we start with are still there at the end. So the mass shouldn't change. Start with 8 particles, end with 8 particles. Just rearranging them a little bit. Did we form a precipitate on that one? Not that one, right? What about station 3? That was steel wool pull apart. What kind of change would that be? Physical. All right. There's no evidence for a chemical change, right? So just a physical change. In station 3, all we did was change the shape of it. What do we expect the mass to do? I think our class data showed that on the steel wool pull apart that the mass decreased. But I think that was an error. It should have stayed the same. Okay? Is that okay? Is that okay? Oh, I didn't put the measure. Okay, so yeah, we had some different measurements. I can only think of, I noticed some groups like zeroed it when they got there. And it might have made some changes. I don't know. Another thing that could have happened on station 2, by the way, is you could have noticed a gain. And that's because on that, particles, water particles in the air around the beaker could have condensed on the outside of the beaker because they cooled down. So if we notice water on the outside of a cold glass, which we haven't really talked about yet, but there could have been a gain in mass with condensation. Okay, so in station 3, we already said physical change, the mass should have stayed the same. All right, so all I did here was I made a box to represent the steel wool. Obviously, that's not the real shape of the steel wool, but it's just a model. So I started with 6 particles. Okay, so I have 6 before. And then after, I made it into 2 separate pieces looking like they're ripped. Each one has 3 particles. So there's still a total of 6 particles at the end. So start with 6 particles, end with 6 particles. See how I'm not using a ton of dots. I'm just doing a representation, and I'm making it easy. If I make like 30 dots, it makes it harder to tell what's going on. Then I have to also make sure I count them all up. Whereas making 6 dots is pretty easy. It goes pretty quick. Also, somebody looks at it, they go, okay, there's 6 in the before picture, there's 6 in the after picture. They're showing that the mass didn't change. Looks like the only thing that changed was the shape and size. And I just said steel wool particles, just made them black. Okay, now showing a decrease in mass on this, probably because we had steel wool stick to our fingers or fall off the watch glass. So obviously in the real scenario, we're kind of losing some of the particles. Okay, in the real scenario, it might have been that there were only like 5 dots here and maybe 1 dot that fell off. Okay, that's a possibility. Cool. Okay, so in station 4, we actually burned the steel wool. So what would that be? What would that be, chemical or physical? Chemical, combustion. Yes, we're burning something. All right. Now, whereas with the wood split, you might have noticed like smoke leaving and things like that, you probably didn't notice that as much with the steel wool. So this is an example, and it's an important example because you guys are going to see this on your quiz. Shows up. This is the only station really where the mass may have increased. I know it didn't really much with our data, but we were dealing with small amounts, and there's always going to be some error with measurement and precision. So what I did in this situation here is I made my steel wool. I just used 4 dots in this one, but I also included oxygen because oxygen is important for combustion. All right, so I put the oxygen out here as red dots. And then what I'm going to have it do, since it's a chemical change, what I can do is I can rearrange the particles, I can break them apart, I can join them together. So in this case, what I did is I just took those oxygen dots and I combined them with the steel wool. So obviously this is an exaggeration. The mass didn't double, but according to my model, it goes from 4 dots that are actually being on the balance, because the balance would be finding the mass of this part, to now 8 at the end. So it doesn't really double, but just to show the idea that oxygen is combining with the steel wool. So this would show 4 going up, increasing in the number of particles, mass increased. So that's what you're going to get. Maybe you get a quiz question that shows you data that shows a mass increase during a change, then you're going to know it has something to do with burning something. Oxygen coming from outside in. Okay, station 5 was sugar being dissolved in water. What kind of change do you think that is? It is just a physical change. We're just making a mixture. That's all we're making. Now, what do you think? Should the mass have increased, decreased, or stay the same? Stayed the same, right. We're just taking the sugar and adding it to the water. All right. So I put physical, same, and now I had to show the 2 types of particles we had at the beginning. I just made 4 H2O particles as blue. I made 3 sugar particles as red. That's my before picture. And then in my after picture, I just combined them all. So when we dissolve something, what we really do is we just take a certain chemical that's in large clumps, large group of particles, and the stuff that we're dissolving it in just breaks it into smaller parts, but it's still the same type of particle. How can we tell? Is there a way to tell that this is still sugar in there? How? Drink it, that's right. We would never drink out of lab equipment or in a lab, but you can probably imagine, if you've ever had Kool-Aid or anything like that, if you put sugar in the water, it dissolves. It looks like the sugar disappeared, but if you still drink it, it tastes like sugar water, right? Possible error. So when we're combining these things, these combination stations, it's easy to not zero the containers if you see that in the bottom right corner. Um, Not adding the two substances together at the beginning was a big mistake. So a lot of people didn't realize that the total mass before was actually the mass of the sugar plus the mass of the, mass of the sugar plus the mass of the water. Okay, we should have combined those for our mass before and then compared it to the after. And it should be the same because all we're doing is just mixing the particles, that's all. Just mixing them together. Again, I need to pay attention. I don't do this with all the models because I was kind of going quick last hour when I was drawing this. But I should always like label the beakers, label the big things. And then we went to station 6 where we combined baking soda and vinegar. What kind of change did we have there? That's a chemical. How do we know? There's what? No change in the size. Was there a change in the size though? What happened when we combined them? What did we see? Yeah, it bubbled up, right? So when we see bubbles produced, that's an indicator of a chemical change. All right. So on this one, what I did was I put chemical change and I said the mass decreased. And here's why. So at the beginning, I just made 3 baking soda particles. I decided to make them green. And then I made vinegar blue, made 3 of those also. So my mass before is really going to be 6 particles. All right, now when I combine them, all I did was I just stuck them together because it's a chemical change. Okay, so as you can see here and here and here, I just stuck them together to make a new substance. All right, so open system and closed system. There's a reason why I made these asterisks next to it. Very, very important to understand these. You'll be asked about these. A closed system means that particles cannot enter or exit. An open system means that particles can enter or exit. It's open. So particles can come in from the outside, they can leave. Closed system particles cannot. So at station 6, particles are actually leaving. That's what the gas bubbles are doing. Going towards the surface, bubbling up, and leaving. So if we look at this after drawing, and this is important when we model this stuff as we continue on, I started with 6 particles. I still have 6 particles at the end. But in terms of what we're finding in the mass of, In my depiction here, we're only finding the mass of 2 particles. So it looks like the mass went from 6 down to 2. Now, it's not that particles disappeared, it's just that they left. They went into the air, and if they're into the air, we're not going to be able to find the mass of them with a balance. All right? So this would be an open system. Burning the wood splint would be an open system because the oxygen was coming in, remember? Melting ice, I mean, it was an open system, but it doesn't really matter. Just closed system. Steel wool pull apart, closed system. The particles that are there are the same ones the whole time. But burning steel wool, open. Sugar combined with water, closed. Nothing new coming in from outside, nothing leaving. Baking soda and vinegar, particles leaving. So this has got to have an open system. What do you think would happen here if I combined them and really quick put a lid on the top? Do you think the mass would still be the same at the end? It should be. Okay, the particles aren't disappearing, they're just leaving. So if I prevent them from leaving, they should still be in the container, which means we can still find the mass. All right, made station 7 really easy for you because that was Alka-Seltzer and water. And really, that's the same exact concept as station 6. So I just put station 7 equals station 6. Okay, again, another error here. Combining things, it's easier if we get to 0 or account for different containers. Some may have stayed behind when we were trying to combine them. Same for with the sugar in the water. If we find the mass of the sugar and then we pour it into the water, maybe we didn't get all the sugar particles out of the little beaker. But Alka-Seltzer, we put that into water. We saw bubbles, indicates a chemical change. The bubbles are leaving the system, so we're losing mass. The mass should go down there. And then station 8, our last station, you ready for this? So station 8 was a chemical change. We could tell because of the formation of a precipitate. Okay, we combined 2 clear liquids. They got all cloudy because of precipitate, a solid formed in there. Little bits of solid particles forming in there made it all cloudy. The mass, however, should have stayed the same. No particles were leaving, none were entering. The particles I started with, same thing as what I had at the end. But since it is a chemical change, I did go ahead and stick the different types of dots together. So in the beginning, I started with a total of 8 particles. At the end, I still have 8 particles, which means mass is the same. In this first drawing, I just made 4 calcium nitrate particles. I made 4 sodium carbonate particles. And then the after drawing, I just stuck them together in one container. So the main idea with all of this mass and change stuff, we learned about different types of changes. We learned about mass. We practiced with mass, finding the mass. But the main idea is that when we do models, and this is going to be another norm that we always got to make sure we pay attention to, the number of particles in each drawing should never stay the same. Should always stay the same. If I can draw particles like outside of the container in the air, that's fine. I can draw them in the container, but however many particles I have in one picture, I should have the same number of particles in the other pictures. Yep, so same number of particles before and after if it's the same. If the mass increased for some reason, then at the end I would have more particles, but then I would have to go back and say, where did those particles come from? And I'd look at my before drawing and say, maybe I had to draw some in the air. Maybe they came in from the air somewhere else. If I have less particles at the end, then I got to say, where did they go? Maybe they went into the air. Maybe they escaped into the air like in station 6 and 7. So I would have to draw them outside the container going into the air. I'd still show the particles though. So what this is called is the law of conservation of mass. Okay, and this is the end of the notes. So the law of conservation of mass, again, another star next to it. This is the main idea from this whole mass and change lab we did for a week with the modeling and everything. Matter cannot be created nor destroyed by chemical means. So when we have chemical reactions, all the matter that we have there to start should be somewhere at the end. It doesn't just disappear. It doesn't appear magically out of thin air either. So whatever we start with, we got to have at the end. What's that mean in terms of models? As I said here, this is a norm, conservation of mass, conservation of particles. It means however many particles I have in the before picture should be equal to the number in the during, which should also be equal to the number of particles in the after picture. They should all have the same number of particles. They can be different types of particles. They can be rearranged. They can be stuck together. They can be broken apart. But however many particles I have in the first picture, it has to be the same in all the pictures. Does that make sense? And that is the end of the notes. So next, I'm going to give you guys an opportunity to work on your own. I'm going to give you a little worksheet. It is due by the end of the hour. It doesn't take very long. It's just going to go over everything that we just talked about on these notes.